Hello, everyone, and welcome to our virtual Astronomy Day program here at the North Carolina Museum of Natural Sciences. My name is Nancy, and I will be your hostess for this very special talk, Space as a Time Machine. And it will be presented by students from the University of North Carolina. And usually, if you have done this kind of programs with us before, you know that we like to start off with an icebreaker question. So, we would like for you to type in the chat. Where and when would you like to go if you could go into a time machine and go back in time? And you can write that in the chat. And while you are doing this, we are going to go over a quick Zoom tutorial. I know you're all experts by now, but it's kind of like a little refresher. And we can also show you a few of the features that are available. So first of all, this program will be recorded. So that means that everybody's speaker will be muted and the videos will be turned off. But closed captioning is available. So just click on that little CC button in the bar below, and then it will click on show subtitles. And then when you do that, you can actually go all the way down to subtitle settings and change your font and things like that. Now you can see that our guests and our speakers are kind of obscuring the slides. So what you now need to do next is go and click on the gallery view and change that into speaker view. And then when you go to a few options and you scroll all the way down, you see that little side-by-side mode. Click on that. And when you do that, our speaker will be in a little box next to the slides. So then, of course, you can adjust the size of the slides by just moving the slide bar either to the left or to the right. And then last but not least, we want to hear from you. We want to have this very interactive talk because we have three speakers here today. So if you have any questions or you have any comments, please put them in the chat. We have somebody who's going to monitor the chat for us. And so what we do ask from you is to be just good digital citizens, right? So don't spam the chat and be respectful to our speakers and our moderator as well. So with that, I'm going to stop sharing my screen here. And I would like to ask our students from the University of North Carolina to introduce themselves, tell them who they are, what you're studying right now, and how you got into becoming, into that field of astronomy. And maybe I can ask Raleigh to go first.
Hi, my name is Riley Milburn. I'm a third-year graduate student at University of North Carolina, Chapel Hill, and I study exoplanets, that is, planets outside of our solar system, and specifically very young exoplanets, because I'm interested in learning about planet evolution at its earliest phases. I got interested in astronomy when I took my first astronomy course in college, actually, so not too long ago. And what I really liked about it was being hands-on with a telescope and actually looking up at the stars.
Yeah. Mega, you want to go next?
Yeah, sure. My name is Mega. I am a third-year undergraduate student at UNC Chapel Hill. I first got interested in astronomy when I was in high school. I went to Zion National Park, and gosh, the stars that you can see there, just because of the lack of light pollution, it was amazing. And I was like, I want to do this for the rest of my life. I think, was that it? I think that's the answer all the questions.
No, that's good. And how about you, McKenna?
Hi, everyone. My name is McKenna. I'm a fourth-year grad student at UNC. I'm also studying exoplanets, specifically exoplanets in star clusters, and then I also study the clusters that they're in. I got really interested in astronomy, I've been a bit interested in my whole life. Space is really cool, and I grew up in a really dark sky area, so I got to see that pretty much every night, and that sort of started my interest in astronomy.
Very good. Thank you so much. Well, I'm going to ask Raleigh just to take it away, right? Okay. So if you want to share your screen with us, thank you.
Okay. So hello, everyone. Welcome to our talk, Space as a Time Machine, where we're going to run through how we can actually use light, time, and the greater universe to understand what things were like a long time ago and sort of understand how things came to be. I'll let McKenna start off for us.
Yeah. Hi, everyone. So sort of the big picture point of our talk is that as astronomers, we can't watch things change in real time, since the vast majority of astronomical objects are very old and change very slowly. So to study how things like planets or stars or galaxies change over time, we have to sort of look back in time. Fortunately, that's really easy for astronomers to do, since light travels at a finite speed, and we can see the light that came from millions or billions of years ago by looking at objects that are very far away from us. So sort of to look at some of the astronomical objects that astronomers look at, we look at planets, and to form a planet, to go from taking, just a bunch of dust circling a star to sort of a whole planet like Earth. This is a very open question in astronomy, but we think it takes about 5 million years for that to happen, just to form the planet. Whereas if you look at something like a galaxy, that takes even longer to form. So we think that galaxy formation takes somewhere around like 1 billion years. Again, these are open questions in astronomy, but we think that we think that galaxies really started forming about 1 billion years after the Big Bang. So it takes a very long time for galaxies to form like that. Supernova, however, are the outlier here. Astronomers who study supernova get really lucky because supernova only take a day. They're very fast. So supernova are the one thing that we as astronomers can look at and see it happen in real time. On the other hand, something like stars, most of what astronomers look at are stars. Stars take the whole lifetime of a star is somewhere between 1 million or tens of billions of years. There are stars that are tens of billions of years old, and we don't know when they're going to die. They just keep going. They're very, very old stars. And to compare all that, an astronomer usually lives to, let's say, about 85 years old. So in the average lifetime of an astronomer of 85 years, it's very, very difficult to learn anything about stars or planets or galaxies unless they go supernova, and then we can look at them. So how do we study these things? How can we learn about planets and galaxies and stars if we can't ever watch them change in real time? The answer is that we use our time machine. So in this case, our time machine is not an actual machine that we can climb into. It is light. So light travels through space. And to sort of talk about this more, I'm going to use the analogy of news traveling across the world. So imagine if I want to know what's going on in the world and we don't have the internet. So in order to learn what's going on in the world, I call up people in all these cities and I ask them to send me a newspaper. And that newspaper physically has to travel from whatever city it's in to me in Chapel Hill. And this is just like light. Light physically has to travel from whatever things we're looking at to us. So the newspaper has to come from these cities. And it's going to take a different amount of time depending on what city it's coming from. So it doesn't take me very long at all to get a newspaper from Raleigh. So if I asked for a newspaper from Raleigh on January 1st, I will get it the same day. It's right there. They can get my newspaper to me pretty quick. But if I ask for a newspaper from someplace further away, like Santiago, Chile, that will take a day or so to get to me, maybe. So I might get the news from Santiago on January 2nd. Someplace further away than that, somewhere in India, I might take 2 days to get there. So I get my news from there on the 3rd. And then from all the way on the complete other side of the world, my news from Australia might take 3 days to get to me. So that I would get news from Australia from the 1st, I would get it on the 4th. So now imagine if instead of just asking for newspapers on the first and getting them as they came in, I asked for a newspaper every day. So every day a newspaper left each of those places and it traveled to me in Chapel Hill. What newspapers would I get on January 5th? So on January 5th, I know that the newspaper from Raleigh takes 1 day to get to me. So I'd get that same day. I'd get the January 5th news on January 5th. I know that it takes 1 day for the newspaper from Chile to get to me. So I'd get on January 5th, I get the January 4th edition of the news. I would get the January 3rd edition of the news from India on the 5th, and from Australia all the way on the other side, I would get the January 2nd news on the 5th. So on this 1 day, I get news from 4 different days because I am getting news from 4 different places. So by looking at these different places, I can get news from different time. I can see what happened 3 days ago in Sydney. Sort of the same thing applies on a universal scale. So the universe, we look out at all of these objects and we get light from them that left a different amount of time ago, depending on how far away they are. So within our solar system, we can get information, pretty much right on time. The distance that it takes light to travel from Mars to Earth is about 3 minutes when they're closest together. It gets a little bit longer if Earth and Mars are further apart, but at closest approach, it's 3 minutes. So this is kind of important for things like controlling NASA's Mars rovers, because if they want to send any information to the rover and then get information back, it takes 3 minutes to get there and 3 minutes to get back. So we are getting information always from 3 minutes in the past from Mars. If we look a little bit further out into the galaxy, we can look at, say, something like a star cluster that's more distant. So, for example, the Praesepe star cluster is about 577 light years away. So when I look at that, I am getting light that left there 577 years ago. So many of you I saw in the chat, a couple of people said that they wanted to go back in time to pre-Columbian days in North America. So the light from the cluster here left back in those pre-Columbian days. Next, we could look at something outside of the Milky Way galaxy. We could look at, say, the Andromeda galaxy, which is our nearest galactic neighbor. And the light that we see from Andromeda left 2.5 million years ago. So when we look at Andromeda, we are seeing 2.5 million years back in time. And we can go even further than that. So there are things called galaxy clusters, which are just groups of galaxies, and they are pretty far out in space, most of the ones that we can see. So something like the Abell galaxy cluster is 4 billion light years away. So when we look at this Abell galaxy cluster that we've got a picture of here on the far right, that light came 4 billion years ago. So just about the time that the sun was forming is when the light left that galaxy cluster that we are seeing right now. So we can use the light from around the universe to be able to sort of see back in time. And now I am going to hand it over to Riley, who is going to talk about how we can use that to study planets.
Thanks, McKenna. So as McKenna noted, astronomers use their tool, light, to peer into the past, sort of like a time machine. And one application that I think is really cool is using light to study how planets evolve with time. So when people think of planets, I imagine the first planet they think of is our Earth. The Earth is very special to us. We live on it. It's our home. And aside from that, it's very tangible because we're here right now. We know what a planet is like because we live on one. Now, some facts. The Earth is 4.5 billion years old, which is pretty old, especially when you put that into in comparison with how long humans have been around. So modern Homo sapiens evolved around 300,000 years ago. Modern Homo sapiens being humans like us, people, 300,000 years ago. Now, if you were to condense the entire life of the Earth into 1 day, that is all 4.5 billion years that the Earth has been around, if you condense that into 1 day, people like us have only been on Earth for around 5 seconds of that 1 day. which is minuscule, so small. So there's no way people just being on Earth could have watched the Earth form or really watch it evolve with any significance, at least in great detail. However, we aren't entirely clueless. On Earth, there are some tricks to learn more about the past. For example, we can sort of study the various layers of the Earth's crust and piece together a fossil record, as well as use various dating tools. This is typically what geologists and archaeologists do. They study layers of the Earth, different rocks, different fossils, and they can radiocarbon date those things. And they have other methods of dating to tell them things about like the formation history of the Earth, even the climate at different time periods. One great example that you're probably familiar with is the Grand Canyon. So if you look at the Grand Canyon, you'll actually be able to notice these distinct bands. And these are just, as the Earth has been around, forming, evolving, you know, layers just sort of stack up on top of each other. And so the farther you go down, the earlier in time you're looking. And so the Grand Canyon is interesting because at its most bottom level, you can actually learn things about the Earth up to billions of years ago. The entirety of the Grand Canyon, we think spans a time frame of 600 million years, which is far greater than humans have been around. And we can learn a lot about the past that way. And, you know, as I mentioned, fossils, there are also fossils in the fossil record that we can use to sort of study what life might have been like, what living things were like on Earth a long time ago. But again, these things aren't living right now. We're making a lot of inferences based on what we can see right now and in this record. But of course, you know, the Earth isn't the only planet. There are lots of planets in our solar system. Not all of them are like the Earth. And not only that, we can really only looking locally at our solar system and the Earth, we can only really piece things together from when the Earth had already formed to today. So this is where astronomers come in, where we use our light, our time machine to really piece together, well, how did the planets get here? How did the entire solar system get here for that matter? We want to know before the Earth was even here. This is where light comes in. And so I'm going to run us through okay, so what if we want to learn how the solar system got here, how the planets got here before it was already formed? We want to look beyond. And so I'm going to run us through basically solar system formation and talk about how astronomers think the solar system formed, how stars form, and then how the planets form around it. And then how astronomers actually observe this with their time machine and piece together the puzzle. So just starting here, big picture, let's run through how the solar system actually forms. A solar system. So we start here with interstellar medium. Interstellar medium essentially is just gas and dust in space. It's very spread out. It's very diffuse. It doesn't really have a lot of structure. It's just kind of floating out there. But over time, that gas and dust can start to cool and clump together gravitationally. It gets more dense and packed in. And as it does that, it'll start to form what we call a nebula. Basically, this is the same. It's still gas and dust, but there are regions that are cooler and denser than others. We call these regions overdense regions. These are regions where the material is getting very close together, very packed, and then there's still some of that diffuse areas around it. But it's in these overdense regions, these packed together regions that we care about, because over time, they can get so packed together, so dense, that the atoms that make up that gas and dust can actually start to come together, to fuse and bond. And that's what ignites a star. That's how stars are formed. So once we have a star, we then have this big, massive structure in this gas and dust. And that causes the rest of the gas and dust left over to sort of gravitate around that star and form, because gravitationally, this is a preferred orientation. It starts to form a disk as it rotates. And it's in this disk, actually, that the extra leftover gas and dust from when the star was formed actually starts to clump together itself. And it's in this clumping together as it orbits and collects more and more that the little gas and dust outside actually starts to form planets. And so the planets are formed from this extra gas and dust in what we call the protoplanetary disk. And, you know, this process in whole, as McKenna noted, can take millions to billions of years, depending on the lifetime of the star. So there's no way that in real time we could actually watch this happen. But fortunately, we have computer simulations that help us visualize it. So I'm going to play this video really quick and run through what it looks like in real time, a solar system to form. So here's our gas and dust. As you'll notice, it's gravitating around itself. It's clumping together. So in the middle, it's very shiny. We have that over-dense region, the region with lots of stuff packed together. It's not quite a star yet. Right now, it's still just growing in size, collecting all of the gas and dust, growing. You'll notice it's getting more diffuse out here. And then boom, it ignites, it starts fusing, it becomes a star. And in becoming a star, the things around it start orbiting gravitationally more intense. And you'll notice here, if you can see, the planet's actually starting to form. So there's this clumps of matter. As they go around, they're essentially snowballing, collecting more and more material until finally they themselves become planets. They don't have enough mass to become a full-fledged star like at the beginning, but they become planets as we know them today. And, depending on how close to the sun or far away versus, and also how much mass it actually ends up collecting, can tell us properties about what that planet is like.
This is such a great visual, Riley. And I'm sorry, I didn't want to interrupt you, but we do have a few questions. And I was wondering, would you like to see if you can answer some of these questions? Or should you wait until the end?
I think the end might be better, if that's okay.
We will do that.
Thank you so much.
Thank you.
Okay. So as I mentioned, this is the picture, but so it's up to astronomers to actually use light, our time machine, to sort of piece this together. The real thing, not the theory or the simulation, And so this is stage one, essentially. This is an observation that astronomers have of the Eagle Nebula. As we mentioned, a nebula is the cold and dense gas and dust where stars are formed. This gas and dust is made of interstellar, sorry, never mind, I already said that. It's mostly hydrogen. These regions are 1 to 2 million years old, which in the grand scheme of things is pretty young if we consider the age of the universe being about 14 billion years old. This is only 1 to 2 million. That's a significant fraction younger. This is like the earliest stages of planet formation. And the Eagle Nebula is actually an active forming star region. There's stars that we think are forming today. Granted, as McKenna noted, it's, I think, around thousands of light years away. So the light that we're getting today is actually thousands of years old, but still almost today in the grand scheme of things. This is another example of a nebula. This is the Orion Nebula. The Orion Nebula is around 3 million years old. What I think is interesting about the Orion Nebula, though, is that we actually have observations in the Orion Nebula of protoplanetary systems. That is the disks where there are like what we would call planetesimals, or just forming planets. Not quite a planet, but it's that object out there in the gas and dust that's sort of spinning around, collecting gas and dust, and will eventually become a planet. And what does a protoplanetary disk look like? Well, we can observe those too. Here's what a protoplanetary disk looks like from the eyes of an astronomer. I want to just point out, in the middle of these diagrams, there is a shape that looks like a star. This is not what a star actually looks like. That's just to help us know where the star is. The star is actually spherical, round. But what I like about these pictures is that we can actually start to see the rings or the banding structures where the planets are forming, right? We saw in the simulation that there's little planetesimals orbiting around, carving out their orbit in the gas and dust. And that's exactly what's going on here. The light regions are the gas and dust, and the dark regions are where the planets are actually orbiting around, collecting that gas and dust and growing bigger and bigger with time, forming the planets as they are today, which looks something like this. This is a full-fledged solar system, not ours, but one elsewhere, where we can see planets orbiting around a sun. This image is taken over the course of a few years, so they're moving pretty slow, but those planets are out there and they're moving, they're fully formed. And so just wrapping this all up, we got to piece the puzzle together. We have observations of the various stages of planet formation, but we can make inferences from each one based on how old the things are to sort of piece together how planets form, how the solar system forms. This is essentially our time machine, where we go back in time to look at the early stages, then the middle stages, and the late stages. Now, this timeline is pretty broad. It's up to astronomers to fill in all the tiny minutia and detail that goes in between every little step. And that's sort of related to what I do in my own research. I study very young planets, so I'm interested in the earliest period of planet evolution after it's formed. Specifically, I'm curious as to why it seems that young planets that are very big and close to their stars seem to be losing a lot of mass early on in their lifetime. And we think that might be caused by this process called photoevaporative mass loss, which is just to say because the planets are so close to their stars, which are pretty active because they're pretty young, the stars are actually blasting the mass of these planets away early on in their lifetime, which causes them to go from really big to pretty small early on. And so that's something that I'm interested in studying, and hopefully we can piece together more about that. But astronomers are studying planets of all different stages to sort of piece together this greater picture of like, how do planets form to how do they look today. I'm going to pass it back to McKenna now to talk about other types of time travel.
All right, thanks, Riley. So yeah, planets are really cool, but they're also pretty small on a galactic scale, which means that they're hard to see, and we can only look at planets that are pretty nearby. So the most distant exoplanet we've ever discovered is about 27,000 light years away from the sun. The universe is 14 billion years old. So being able to see 27,000 years back is pretty much nothing. In order to see further back in time, we've got to look at distant galaxies instead of planets. So one of the reasons that astronomers like to look at galaxies is because we can see really far back in time with them. And when we do look at galaxies, we see that galaxies come in many different shapes and sizes. So up here, I've got 6 different pictures of galaxies going from left to right. We've got a spiral galaxy, like our own Milky Way. It's got these sort of spiraling arms that come out from the center. Then an elliptical galaxy, we call it, which is basically just a blob. It's a blob of stars and gas and stuff. The next one is what we call a barred spiral galaxy. It's like a spiral galaxy, but it only has these 2 sort of arms and a bar going right across the center. Then we've got sort of weird galaxies on the bottom, like this, it's called a ring galaxy. It looks sort of like a bullseye. There's a bunch of stuff at the center, gas and stars and all sorts of stuff, and then a whole large area of pretty much nothing, no stuff at all, and then there's more stuff sort of surrounding a ring on the outside. So it looks sort of like a bullseye, which is sort of a weird formation for a galaxy to be in. Why isn't there any stuff in that middle region? Then we've got galaxies like this middle bottom one, which are super actively forming a lot of stars. They're doing a lot of stuff. And so it's shooting a ton of material out from the center, which is what you can see in this red sort of jet coming out from the center. It's really active. It's doing a lot of stuff. And then last here, we've got 2 galaxies that are sort of right next to each other. They're sort of gravitationally interacting, and you can see that they're developing sort of little like wisps and rings sort of around the center. So we've got all these different types of galaxies, and they look weird. So astronomers wonder what makes them look like that? What made the Milky Way galaxy spiral, and what made others look like bullseyes or blobs? So we want to know how these galaxies formed and how they change over time to get all of these different shapes. Yeah, and one of the things that we have learned from looking at these galaxies that we can predict based on the movement of our galaxy and the Andromeda galaxy is that someday they'll crash into each other, mixing up all the stars and the gas that each of them has and significantly changing how they look. And so we've predicted that Andromeda and the Milky Way will do that someday. And then we looked out into the universe to see if we could find any other galaxies that have done that or will do that. And we actually found a lot of them. So there are plenty of examples we found of galaxies that are in the process of colliding or have just collided. And we, in fact, have so many examples of these that we can look at them and we can start to compare them to our models to form a sort of a really good idea of how different galaxies formed. So these 2 pictures on the left are real images of galaxies in different stages of colliding. So the one on the further left, you can see we've got this galaxy on the top and the galaxy on the bottom, and they're like just starting to collide. And you can see this sort of string of material connecting them as one galaxy pulls material off of the other one. And we compare that to sort of the models that and the simulations that astronomers can do over here on the right. We can see that that looks sort of just at the beginning of this loop when they start pulling each other sort of out into longer bits. And that's what's going on here in this actual real image of galaxies colliding. Then in the middle sort of picture, we have a picture of galaxies that are much more like further along in their collision process. So you can see, you can still sort of make out the two centers of the galaxies. There's the one in sort of the upper diagonal and then the one in the lower diagonal, those two bright spots. Those are the centers of what used to be two distinct galaxies. And now they've sort of collided, mixed up all their stars, mixed up all their gas, and you can't really tell them apart as much anymore. And this looks like, if you look at this looping image, sort of just right at the end, if you look just at the center, you can see how there's sort of two centers left there, but they're all mixed together, and that's what we're seeing here. So by looking sort of back in time, we can find different parts of this collision process in different galaxies that are colliding all over the universe, and we can use that to learn how these sort of collisions shape the way that galaxies are. But another reason that galaxies are really interesting for astronomers to look at is, like I mentioned before, because they're very far away. So we can look very far back in time with them. We can learn about how the universe was billions and billions of years ago. But how far back can we go? So this is a little bit tricky. It's very hard to see things that are far away because they are very far away. They get smaller, they get dimmer as they're farther away. So you need a bigger telescope to see them. And you also need a telescope that can see infrared light, because the light coming from very far away objects tends to be infrared. As it travels very far, it gets redder and redder. So we need a very large telescope that can see infrared light. And lucky for us, the leading edge of astronomy is the James Webb Space Telescope, which was just launched this Christmas. It's the biggest space telescope that has ever been made, and you can sort of see in this image how big it is. It's 6 meters across. You can see this is the mirror of the telescope. And then down here on the right side, you can see these people over here. They're little people compared to the telescope, which is huge. So it's a very large telescope. And it also is designed to be able to see that infrared light. So it will be able to see the formation of the first galaxies ever made, about 13.5 billion years ago. And those galaxies, they were formed and the light left them only about 400 million years after the Big Bang. So we'll be able to go back almost as far in time as we've ever been and learn about the formation of the very first galaxies and learn about the early universe like that. It's going to be really cool. I'm very much looking forward to the awesome science that is going to happen as soon as the James Webb Telescope is ready to go, which will be in just a couple of months. So that's really cool. I'm going to hand it back over to Riley now.
All right, so we've been talking a lot about time travel and looking at stuff in space, traveling back in time, but I thought it'd be fun if we could maybe do some like time travel here on Earth. Would it be possible? One question that I have if I could time travel is I would like to know what a dinosaur looks like. I really like Jurassic Park. I like movies with dinosaurs. I think dinosaurs are awesome, but we don't actually know what dinosaurs look like. We only have their fossils. So could we use this time machine that we have, light, to study if dinosaurs were in space? That is, if light travels at a finite speed, could someone see a dinosaur with their own eyes? And in theory, yes. In theory, yes, although it gets a little complicated. But let's run through this exercise of using our time machine to do some serious time travel to learn what the dinosaurs were like. So dinosaurs went extinct about 65 million years ago, which is a long time. And so what that means is light from the dinosaurs, like light traveling from Earth from the dinosaurs, will be 65 million light years away right now. So that means that if we look at this diagram here, if we're here, light from the dinosaurs will now be about at the Virgo cluster, 65 million light years away. Now that's huge. Our solar system is only like 1 light year big if you go from like the sun to Pluto. This is 65 million of our solar system all the way out here. We have never detected any planets out here. But for fun, let's say that there were a planet out here and there were people on it. Could those people see a dinosaur? Well, it's true that the light would get there. If they wanted to actually see a dinosaur, though, what would they need? They'd need to build something to see it. They need a telescope, right? So they need to build a very big telescope. One big like if you wanted to resolve a dinosaur, it'd have to be huge. For perspective, the world's largest telescope on Earth is FAST. It's a radio telescope, and it's 500 meters in diameter. That's like the length of 5 whole football fields you could fit in that dish. A telescope that you wanted to use to observe dinosaurs would need to be about 4 light years in diameter. That's 4 whole solar systems in that whole telescope. That's humongous. And unfortunately, if you consider the materials that you might use to make a telescope, the mirror is probably going to be made of glass. So something that large would certainly collapse under its own weight. Just to give you an idea, if you made a structure of glass, of the density of glass to be about 28 light minutes, how long it takes light to travel 28 minutes, that would collapse in on itself and become a black hole, actually. So this telescope would certainly become a black hole. And so, unfortunately, while the light from the dinosaurs would be there, what you would be seeing is nothing at all, because your telescope would have turned into a black hole and you would be sucked in and you wouldn't see anything because light cannot escape a black hole. So while, yes, the light from the dinosaurs is traveling, I do not think you would actually be able to see the dinosaur unless you could break the laws of physics. Or one other way is if we could actually physically time travel. So on that note, I'm going to switch over to Mega, and she's going to tell you about some more physical time travel that we can do in physics.
Okay, hi. So we've talked a lot about how space can be a time machine, but the thing is, for actual time travel, we'd have to travel at or close to the speed of light, which is very hard to do. But if we could actually do this and time travel in the future, we would have to worry about something else called time dilation, which is basically when you move at these speeds, time will eventually slow down. So what is time dilation in general? In general, it's the difference in time between 2 clocks, and the 2 clocks in question are stationary clocks, which are the ones just standing still, and a moving clock, specifically one moving at or close to the speed of light. And the basic idea is that the moving clock will always run slower when moving at or close to the speed of light. And why is this? So when looking at the diagram that we have at the top of the slide, sorry, I'm trying to look at where my place is. When looking at the diagram, we have a stationary clock on the left of the image, which is just 2 mirrors on top of each other, single photon, which is a light particle bouncing back and forth between the 2 mirrors, indicated by the red line. And then with the stationary clock on the right side of the picture, or with the moving clock on the right side of the picture, we have the mirrors moving simultaneously at the same time, and the photon, the light particle, has a much longer distance to travel. And so if the red line shows the path of the photon, yeah, we see it has a much longer distance. So why doesn't this happen on Earth when we're in our cars? So on Earth, we can't move even close to the speed of light. In fact, the fastest jet plane that we have moves at about 1,000 meters per second, whereas the speed of light is 300 million meters per second. And if we could go back to the last slide for just a second, the formula at the bottom may be a little confusing with all the letters and numbers, but c is basically the speed of light, and v is the speed that we would be moving at. And since on Earth, our v is so much smaller than our c, then the fraction would basically go to 0, and the time dilation would just equal the time on Earth. So we wouldn't really experience any time dilation at all. So on the next slide, we have a visual showing how the time dilation would work just using a light clock. So the rocket would be moving at speeds close to the speed of light. So you see that the photon has a much longer distance to travel than the one on Earth, just bouncing back and forth. So therefore, time will be much, much slower on the rocket ship, but the passengers on the rocket ship wouldn't feel this at all. And space and time are so closely related to light, and so this is why the time would slow down. And so here we have, with all of this time dilation comes the Einstein's twins paradox, which I think is super interesting. It's with the theory of relativity. And it basically, the twins paradox is that if there were two identical twins, both on Earth, that were the exact same age, if one of them were to leave Earth in a rocket ship moving at or close to the speed of light and then come back sometime later, then the twin who was traveling would be physically younger in every way than the one who's still on Earth. So this is because time slowed down for the traveling twin, but not for the one on Earth. So you can see in the visuals, like the twins are both on Earth, and then the one is traveling, and then the one on Earth is much, much older. But the basic principle behind all of this is that time is absolutely relative. So time is not set in stone. It depends on who you're asking, really. So in conclusion here, we have light and time are very closely related, and it's how astronomers can really piece together how things have changed over time, like a big puzzle. And even though we can't currently use the light to see the dinosaurs with our current technology, maybe someday in the future, if we found out how to move at or close to the speed of light, we could. Okay, is there any questions in the chat or from anyone?
Thank you so much. That was really, really fascinating. Yes, we do have some questions. Some of the questions you already answered, but since we have guests in Zoom and YouTube, I was wondering if we could go over some of these questions because people might be interested in them. So one of the questions was, so how old are most exoplanets?
So exoplanets vary in age, and maybe McKenna can also tag onto this, but exoplanets range in ages from millions of years. There are even planets, billions of years old. I think so. Anywhere from millions to billions of years old would be my answer. It's a pretty broad spread.
Yeah, definitely. Okay. And so you had a very nice visual where you could actually see how all that gas was kind of like drawn to the center. And one of Liz was asking, where did the gas and the dust actually come from?
That's a good question. It's basically just floating out in space from it's just out in the universe. Why it's there is an even more profound question of how the universe even came to be. So
yeah, it's just like interesting how it was kind of like circling around that mass, right? And then you could literally see how it was like drawn from that. It was really cool. So we do have another question from Raina. Is it only a planet after it has cleared its path, or is there another rule separating planets from protoplanets?
McKenna, would you like to take this one?
Sure. So that's sort of a hard question. In astronomy, there's very fuzzy lines between when something is a protostar and actually a star now, and when something is a protoplanet and actually a planet now. So I would say that it is not clearing the path that is the line of that, because then you could maybe call something like an asteroid a protoplanet. It's not really a protoplanet if it's a 4 billion year old asteroid. It's just an asteroid at that point. There's not really a hard line that I'm aware of. We generally start calling things planets instead of protoplanets when they're between 1 and 5 billion years old, because that's when they've sort of finished forming, more or less. I think maybe the best hard line would be that there is no longer what we call a protoplanetary disk, which is that big disk of material out circling the star that was shown in some of Riley's images, and what's left over is just what we call the debris disk, which is what our own solar system has, where there's some stuff, we still have asteroid belts, we still have lots of stuff floating out there, but there's not as much of it anymore. And that's when it stops being a protoplanet and starts being a planet.
It seems like there's a big gray area there. It's kind of like difficult to kind of like define pretty clearly. I also wonder if it depends on where exactly it has been formed and what shape it has and things like that. They're very interesting. And then you had another question. Photo evaporation mass loss is for planets that have not yet had a spinning center producing a magnetosphere protecting its atmosphere, right? Or
Okay, that's a tricky one. I would say it's. I guess I don't even think we would be able to detect if these planets have a magnetosphere. But I guess the point is, if it had one or not, these planets are so close in that the radiation is going to be so intense that nothing can keep this atmosphere on it, essentially.
Right.
Yeah.
Mm-hmm. Okay. I mean, this is so fascinating to me. We have two more questions. So are barred galaxies from multiple black holes forming the center versus one big one? I'm wondering if they mean by this, do you have like a fusion of multiple black holes, or is it just one?
So all galaxies have multiple black holes, which eventually will fuse to create that supermassive black hole that I think you were referring to. We don't think that those black holes have anything to do with the shape of barred galaxies in particular. Those we think are sort of remnants of galactic collisions where you have two galaxies that collide together, and they do it in a very particular way that leaves that it's weird and complicated that you end up with the bar across the galaxy instead of just arms. So when galaxies collide, they have to do it in a specific way to end up with a spiral galaxy instead of one of those blob galaxies, and even more specific way to get specific resonance patterns that move the gas to the center of the galaxy to make that bar across the galaxy. So we think that's our best guess for how we get those barred galaxies, but we're not really sure yet. It's hard to see them form, as we've talked about during this, so we're not 100% sure how those barred galaxies come to be.
Well, and that kind of like leads into the next question, right? Like, what causes the barring specifically?
I think our best guess, based on models that astronomers have done, like that little looping one that I had there, is that you have the gas of the galaxies, that two galaxies are colliding, and as they collide, the gas from them mixes together in such a way that you get sort of a resonance wave through the galaxy, and that forces the gas towards that center bar and into those arms. So that is our best guess right now, based on some of the observations we've had and some of the models that astronomers have done.
Cool. Very interesting. So we also have a very young audience here with us. Neil was asking, does someone get old when they travel back from a faraway planet to Earth?
Everybody will age, but it's the rate at which they'll age that's going to be different. So if that person from the faraway planet was to come back to Earth and traveling really close to the speed of light, or like about half to at the speed of light, then they would be younger than the one on Earth. They'll still age, but at a much slower rate.
I hope that answers Neil's question. And then we also have another question. How do astronomers judge how far away a deep sky object is? I presume we've got the telescopes, but is there anything else that you use? I'm sure you use a lot of computers to a lot of calculations, but I was wondering if you could elaborate on that a little bit.
Yeah. So the way that we tell how far away those really far away objects is we use something called the Doppler redshift. So as light travels through space, because the universe is expanding, the light is traveling through space that is expanding. So think of it like a rubber band. If you took a rubber band and you like marked a bunch of lines on it and then you stretched out the rubber band, the lines would stretch apart farther. So light does exactly the same thing. It is traveling through space that is expanding. So the light gets stretched out. And when light gets stretched out, it becomes more red. So red light has longer wavelengths. So as the wavelength of the light gets stretched out, it becomes more red. So we can look at light from really far away things and say, well, this is, X amount more red than we think it should be. And if it is X amount more red than we think it should be, then it must have traveled Y distance. And that lets us sort of calculate how far away these objects are and how far this light has traveled.
That I like your explanation of the rubber band. That really visualizes that's really good. Yes, we do have another question. So what is the oldest star that you have that has ever been encountered? Does anybody want to tackle that one?
There's one called, and I'm gonna try so hard to pronounce it, but the Methuselah star. I can type it in the chat if.
Yes, that would be nice because I don't want to repeat that.
There we go. That star is about 13.7 billion years old, which is crazy because the universe itself we know is 13.8 billion years old. So very, very, very old star.
That is very old. Right. Awesome. And then Melinda has another question. Will the exoplanets ever grow more? Or do you think they will stay the same? Like once you have exoplanets, can it collapse? What can happen to them?
So I think it's more likely that the planet, as long as there's material around it to collect, will continue to grow. But once it's basically cleared out most of its protoplanetary disk, it's pretty stable. I would say it's possible that it could actually condense in on itself. There are a few mechanisms that would cause it to actually shrink in size, things related to the core, or also mechanisms like I'm researching where the mass is being actually blown away by something. But I don't know of any way that it would grow, unless, of course, it was like collided with another planet, which is possible.
Mm-hmm.
Yeah.
Now, this is so very fascinating to me, and I know that you have inspired so many young, guests here that are with us today. I want to thank all three of you for giving such a wonderful presentation and for being so knowledgeable and just kind of like any question that we had, you were able to explain it so well. So thank you all so much. I also want to thank our guests for being with us today, and of course, our sponsors and our museum members, because without the support of our sponsors and our members, we wouldn't be able to do these special events such as Astronomy Day. So thank you so much. And if you want to become a member, please go to our website, naturalsciences.org/membership, and then you can become a member. And there's all kinds of things that you will get then. There's like 10% discounts when you're buying something from the store, or there's also special events that are just members exclusive. So and then of course you have discounts on movies. So it's a good thing to become a member, and sponsors help us. And then of course we have a lot of talks planned throughout the week. They are free, but you do have to sign up for them. So we are going to put a link in the chat, or you can even go to our website and just check them out, and whatever you think is interesting, just click on that and just register. We would love to see you all. So with that, I think we're at the end of our talk. Thank you so much, Raleigh, McKenna, Mega. That was a wonderful talk. I really enjoyed it, and I know that our viewers have enjoyed it as well. I hope to see you next time. Thank you so much, everybody. Have a good day. Bye.